Okay, so let's start. So in the last class, we were looking at the gamma matrix algebra, and so we'll continue looking at that. I had said that I would do a kind of brief discussion of Lorentz group thing. Unfortunately, I thought I had an electronic copy of my notes, but I don't. So I'll go to my office and get the hard copy. I'll have to actually search it. I don't know where I've kept it because recently I shifted my office. So, but I'll get it by early next week. So maybe my lecture next week, first lecture next week, I'll talk about Lorentz group representation theory, and just as a small interlude, it's not going to take a lot of time. But I also talked to Santosh Rai, and he would also be covering some aspects of Lorentz group. Okay, so hopefully, kind of uh, two pieces together would kind of cover a reasonable aspect of the Lorentz group representation theory. Okay, so I thought I'll do it today, but I discovered that I don't have a uh, electronic copy. I mean, I could have probably typed it, but it would have taken longer time typing that by memory than copying it from the handwritten notes. So I thought I might as well wait. Okay. Okay. So coming back to the gamma matrix algebra that we are looking at, we said that the gamma matrices gamma mu that we are introduced in the covariant form of the Dirac equation, they transform like a contravariant tensor under Lorentz transformations. And we also know that they satisfy the Clifford algebra. This is something we did last time. Okay. Uh, and what we did was that besides having this vector quantity, we can also construct additional in additional objects, additional quantities which transform under Lorentz transformations. And we know that if you look at the anti-commutator, then the Clifford algebra kind of would reduce the anti-commutators of gamma matrices to the metric, but the commutator would survive. Okay, and that is why we said that we could write down these set of products, commutator of gamma mu with gamma nu. This is just appropriate normalization factor, and conventions are kind of different for different cases. I have put a factor of I here when I wrote gamma mu nu. Maybe later in the text we will use something similar, but I will not use gamma mu nu because I don't use I. The purpose of putting I was to maintain the hermeticity conditions similar to gamma mu, namely the one which carries a index 0. So remember, it is antisymmetric in mu and nu. So if mu carries index 0, then nu cannot, and vice versa. So only one of the index could carry 0 index, 0 value. So, but whenever that happens, you would want that fellow to be Hermitian, whereas the other guy is to be anti-Hermitian. Whereas when you do atomic physics, you are looking at components which are spatial, and therefore you would be mostly interested in gamma ij. And if it is part of your problem, you may want to have gamma ij Hermitian, which is opposite of what this convention is. So as you will see later, I would, instead of writing I would just use 1, in fact. Okay. But the reason for introducing it this way is because this is how it will appear in quantum field theory. And that is the place where you will use it much more often than in the relativistic quantum mechanics, like solving hydrogen atom using Dirac equation or something. Okay. Also, second thing is that, like, there is no reason why you should necessarily put I here. There is no reason why you should maintain the same kind of hermeticity conditions that gamma mu had. And therefore, if you want to be consistent everywhere, you could have just put 1 here or somewhere else. Okay, it doesn't matter. Okay, gamma mu nu rho is something that we argued was actually a quantity which is called a pseudo vector. Okay. So I think I mentioned this thing last time, but I think we had not talked about certain discrete symmetries of the theory, of the relativistic theory. So, but I have not written them down either. So, but I'll say these things in words so that it will kind of at least give a flavor of what we are talking about. When I'll talk about the Lorentz group and its representations, I'll probably talk about these discrete symmetries again. But uh, but imagine, like, you're looking at a vector in three space dimensions. Forget about the time component of it, although time component of it will be important when we are going to study the relativistic theory. But let's look at only the spatial component of a vector. Parity is a transformation where you take coordinates xi to minus xi. So x goes to minus x, y goes to minus y, z goes to minus z. Okay. Now, if you do that, then if you have a vector pointing in some direction, starting from origin and goes points in some direction, then that would be written in terms of its the the coordinate values of the arrow, tip of the arrow. And say you are working in Cartesian coordinates, then you would call that as xi hat plus yj hat plus zk hat. Yes. Any question? Okay. Okay. So if you do a parity transformation, then uh, every coordinate will change sign, and therefore the vector would not be xi hat yj hat plus and zk hat, but it will be minus xi hat minus yj hat minus zk hat. And clearly, if you think about this, this would be a vector pointing in the opposite direction. Okay. So therefore, under parity transformation, you expect the vector to change its sign. Okay. That is how that vector would transform. Okay. Now, if you try to write it in terms of 4 vector, then remember our metric convention is 1 minus 1 minus 1 minus 1 diagonally. Okay. So therefore, if you write down a contravariant vector to be, say, t x y z, okay, then a covariant vector would be t minus x minus y minus z. Okay, because of the metric, when you lower the indices, it will flip sign. Okay. So what seems to happen under parity transformation is basically you convert a vector pointing in one direction to vector pointing in another direction in a covariant formulation that takes you from covariant to contravariant. Okay. But main point that I wanted to make was not worry about the covariant versus contravariant, but to realize that the vector changes its direction under parity transformation. Okay. On the other hand, scalar is a quantity which wouldn't change under parity transformation. Okay. Uh, Gamma phi is a scalar. Okay. But scalar in the sense it does not carry any space-time index, but it is not a scalar the way identity matrix is, because this gamma phi contains epsilon mu nu rho sigma, and that would change sign under parity transformation, because out of these four, three of them are spatial indices and they would flip sign under parity transformation. Okay. So therefore gamma phi, in spite of being scalar, actually flips sign under parity transformation, and therefore it is called a pseudo scalar. Okay. So it is behaving like a scalar under continuous Lorentz transformation, but uh, or let me put it that way, this way, that it behaves like a scalar under the class of Lorentz transformations which are continuously connected to identity, whereas it changes sign with respect to a class of Lorentz transformation which are not connected to identity. For example, parity transformation is not connected to identity. Okay. It's a determinant -1 matrix. Okay, because it is diagonally 1 minus 1 minus 1 minus 1, whose determinant is -1. Whereas all the uh, elements of the Lorentz group which are connected to identity would have a determinant 1. Okay. So now we said that gamma mu nu rho can actually be written as gamma mu gamma phi. Okay. Now, strictly speaking, I should really write gamma sigma and then write down epsilon mu nu rho sigma is equal to gamma mu nu rho. Okay. But the point that I want to make here is that this quantity, which is written as gamma mu gamma phi, okay, of which gamma mu part behaves like a vector. Okay, and therefore under continuous transformation of Lorentz group, gamma mu gamma phi would actually behave like a vector. But if you do a parity transformation, then if you do parity transformation, then of course gamma mu would flip sign, but so would gamma phi. Okay, so therefore this vector actually does not change sign. Okay, is this point clear? So an ordinary vector would have changed sign under, at least a special component would have changed sign under parity transformation, whereas, yes.
Excuse me, sir.
Yes.
Sir, in parity transformation, T also changes its sign, sir?
No, not time, only space.
So that we can say the contravariant vector is same as covariant vector under parity transformation. Is it right statement, sir?
Yeah, so it is not same. It goes to that vector.
Okay, sir. Thank you.
Yeah, so vectors are not same, but that is what the parity transformation would do. Okay. Okay, so therefore gamma mu gamma phi has a property that under parity it actually does not change sign, and therefore we would interpret that as a pseudo vector. Okay. Now one simple pseudo vector that we know of is angular momentum vector. Angular momentum vector L vector is written as R cross P. Okay, and under parity transformation the vector R would change sign because it's a spatial vector. If you take x going to minus x, y going to minus y, z going to minus z, R will go to minus R. Okay, but P also would change sign because it is derivative with respect to the same coordinates. So therefore R changes sign, P changes sign. Okay, and therefore R cross P does not change sign. Okay, so therefore we know the example of a pseudo vector even in the non-relativistic case, and that is the angular momentum vector, which is a pseudo vector. Okay, compare that with how the vector P would transform, which would of course change sign under parity transformation. Okay, so that is how these kind of fellows are interpreted as pseudo vectors. Okay, as I said that, like, out of these 15 matrices that we have written down, which are like 4 of pseudo vector type, 4 of vector type, 6 of antisymmetric tensor type, and 1 pseudo scalar. Okay, so these 15 matrices can be written explicitly in terms of polymatrices and identity matrix, and you can check that all these matrices, you choose any particular basis for gamma mu and construct all these matrices explicitly, and you can check that they are all independent, first thing. And second thing, that you will see that they are all traceless matrices with determinant 1, okay, with eigenvalue plus or minus 1. Okay, so that is the property, and therefore there is a lot of redundancy in giving the description of gamma matrices. Everybody has their own favorite basis for choosing gamma mu. Okay, all of them of course depend on what you want to do. Okay, so this is what we discussed some time ago, so I just skip this thing. So we can use this representation to construct various tensor quantities using Dirac spinor. Okay, and so far we have learned 2 quantities. We have seen these 2 quantities earlier. One of them is a Lorentz scalar, which is psi bar psi, and the other one is a Lorentz vector, which was psi bar gamma mu psi. Okay, psi bar gamma mu psi is the one which appeared in the continuity equation. Okay, so these are the 2 quantities we have seen so far. Okay, but now you can replace, this is psi bar psi means psi bar identity psi. That is one of the reasons why I wanted to add that identity fellow, so that I can write down all kinds of tensor quantities constructed out of the Dirac spinor. But this is something we have already seen. Then psi bar gamma mu psi. Okay, and then you can write down psi bar gamma mu nu psi, and you can write down psi bar gamma mu gamma phi psi, and psi bar gamma phi psi. Okay, and this essentially exhausts all kinds of terms that you can write down in 4 space time dimensions. Okay, Of course, if you work in higher dimensions, if you are working in say 7 space-time dimensions, then you would have more tensorial structures available. Okay, but in 4 space-time dimensions, you cannot have anything beyond uh, beyond whatever you have listed: scalar, vector, antisymmetric tensor, pseudo vector, and a pseudo scalar, and that is it. Okay. Now you will see that some of these quantities would appear when you do say a particle physics course, because the interactions of the Dirac spinor with the forces which are mediating various interactions would require you to write down variety of such terms. Okay, they are not all of the psi bar gamma mu psi type or psi bar psi type or psi bar gamma phi psi type. Some of them are of this type, some of them are of that type, some of them are combinations of types, and so on. Okay, and you will need all of them. Well, I shouldn't say all of them, but like, yeah, you will need almost all of them. Okay, even when you study say standard model. Okay, uh, uh, yeah. So I'll leave it at this right now. Okay, so let us now kind of switch over to studying Dirac particle in an electromagnetic field. So we want to study how a charged Dirac particle interacts with electromagnetic field. Okay, of course, if the particle is not charged, then there is no interaction, so there is nothing to worry about. Okay, so our interest, of course, is in the situation where electromagnetic field and a Dirac particle do have interaction. Okay, so we'll follow the same technique, elevate the ordinary momentum to a generalized momentum, and that generalized momentum would uh, tell you that you should replace this differential operator by minimal coupling prescription, which is replace differential operator by a term which involves corresponding electromagnetic gauge field. Okay, so so this is something we have done earlier when we are doing Schrodinger equation, or as well as in the Klein-Gordon equation. This is just a covariant representation, but even in Schrodinger equation, we have done the same. Actually, we have written p minus e minus e times a whole squared kind of term when we studied electromagnetic interactions of Schrodinger particle. Okay, fine. So of course, the in the non-covariant form of the Dirac equation, we will have to of course split these pieces and write them explicitly. So the time derivative of the Dirac wave function would be written as it is. The zeroth component, which is a0, is written out here. I have used the notation capital phi to denote the zeroth component of the gauge field. And this is of course a legacy notation. We have been using phi to denote the Coulomb potential, and I plan to eventually use Coulomb potential at this look as the zeroth component of the gauge field. But you may want to use something else, and in that case, you may just want to write down a0 there. Okay, fine. And then the spatial component would be replaced by p vector is replaced by p vector minus e by c times a vector. Okay, and everything else should remain the same. Okay. Now, if you want to take non-relativistic limit, that is one of the things that we want to do, because once we start looking at theory of atoms or molecules and so on, the velocities involved are small, and therefore we don't want to use this massive, well, not massive, but we don't want to use this relativistic methods, which are elegant but still complicated, and it is better to kind of use non-relativistic techniques and add relativistic corrections to that problem. It gives, in fact, better insight into the problem than actually trying to solve the full non-relativistic problem at one go. Because once you get the answer, you need to kind of keep deciphering what is the interpretation of various terms. Whereas in the non-relativistic case, we'll actually develop piecemeal understanding of every term that we add to the problem. Okay. Anyway, so if remember that psi is written as phi as a small phi as upper component and chi as a lower component, and we are trying to look at a particle interacting with the electromagnetic field and not to worry about antiparticle right now. Okay, And in that case, the lower component, which is chi, would be very small compared to phi, uh, because the energy of the entire system is roughly the same as the rest energy. Okay, non-relativistic limit basically corresponds to saying that kinetic and potential energies are small compared to the rest energy. Okay, so if you do that, then remember we had okay, just give me a minute. I just want to. I just want to get the spinner on the split screen so that we can stare at it while we talk about this one. I suppose we have written it down now. Okay, there. So we used it in this particular form, phi and chi, and we said that the chi would take a form which is like this, okay? That it would be sigma times P minus E by Ca upon mc. Okay, I have kind of gotten rid of factor of C here because I'm substituting E is equal to mc squared. Okay, so therefore it is 2 times mc squared, and one of the c's just get cancelled, so I get sigma dot p generalized momentum upon 2 mc times phi. Okay, so that is what you would get. Okay, this is actually an equality, but nevertheless this equality is actually based on this approximate statement. Okay, otherwise I should have written down the momentum kinetic piece contributing to it and various other terms. Okay.
Sir,
Yes.
in the Dirac equation, it should be plus E phi, right? In the right hand side, in the left hand side, it was IH cross del del
Oh,
T
yeah, yeah.
minus E phi.
That's right. Yes. Yeah. But A0 is minus phi actually. That is how the notation is used. Yeah.
Oh,
Yeah.
A0 is minus. Okay.
Yeah. Yeah. Bad notation, I think. Yeah. Maybe I should. Yeah. Okay. Uh,
Okay,
Sorry. Yeah.
fine.
Yeah. That is the notation one uses somehow. I should have mentioned it actually. Yeah.
Okay, fine.
Okay. So, but like, okay, yeah. I'll try to correct it maybe, because I'll kind of flip sign again at some point. This, yeah, right here, in fact. See, the problem is the following, that what one does is, uh, yeah, maybe I'll just flip the sign. It is easier for me to do that than trying to give this explanation, because the explanation is that, like, you write down A0 as minus phi, and then you say that electron has negative charge, and you flip the sign twice, basically. So what I'll do is I'll just skip that. I'll just put a plus sign here and solve my problem. Okay, is that okay?
Yeah, yeah.
Okay. So what we are going to do now is basically look at this. Sorry, look at this equation, and when we want to take non-relativistic limit, then we are going to say that the lower component is going to be small, because we have made the assumption that the momenta are small compared to the rest mass. Okay, and this approximation is roughly equal to mc squared, tells you that the whole generalized momentum contribution is actually small. Okay, so that is what we will do as we kind of go ahead. Okay, so what we'll do is that we'll use this, plug it into this equation, split this equation into two pieces. Okay, upper component, lower component. Okay, but now lower component equation is not an equation of chi, but lower component is a equation of phi itself. Okay, fine. So use that and put it back into this, write everything in terms of phi. Okay, and as I had said earlier, that you get a 4-component problem in case of Dirac equation, simply because you are converting the second derivative equation with respect to space in the Schrodinger problem to first derivative equation in when you write down Dirac equation. So therefore, you are writing down doubling the number of column entries in the wave function. Upper column is the what you would call Schrodinger wave function, and lower component is basically spatial derivative of the Schrodinger equation. And that is the reason why you see, if A was not there, then you would see that this is just a spatial derivative of phi when you write an operator. Okay, so what we are going to do by doing this substitution is to recover second order form of the equation as far as the spatial derivative is concerned. Okay, uh, in this trade-off, that is what is going to happen. Okay, so what you do is that you substitute that back and you get an equation which almost looks like a Dirac equation. Okay, now of course, sorry, like a Schrodinger equation. Okay, now this is the equation which Pauli wrote down for the first time, and that's why it's called the Pauli equation. Phi is a spinor, 2-component spinor, which could take plus or minus, 1 0 or 0 1 kind of entries, and there are Pauli matrices sitting around here, which kind of says that this solution would have some kind of spin property. Okay, fine. Now we know that Pauli matrices satisfy certain certain equations, has certain properties. We will use those properties to simplify this expression. Okay, one of the property that we would find useful is sigma I sigma j is equal to delta ij plus I epsilon ijk sigma k. Okay, this is something we had talked about last time, so we will try to use that. Okay, so if you use that identity, then remember, when you square this quantity, okay, sigma dot, let's call this entire parenthesis say pi vector. Okay, generalized momentum. So let me just call it pi. Okay, so we have sigma dot pi whole squared. So you write that as sigma dot pi times sigma dot pi, and then you look at only the matrix part of the problem. So that is like sigma multiplied by another sigma. Okay, so you write down sigma dot pi as sigma I pi I, second sigma dot pi as sigma j pi j. Then you get a sigma I sigma j times pi I pi j. Now you use the Pauli matrix identity and say sigma I sigma j is equal to delta ij plus I epsilon ijk sigma k. When you use delta ij, that tells you that delta ij pi j means essentially means that it is pi squared. Okay, that is why you get this quantity pi squared upon 2m. Okay, that pi is of course p minus g by c times a, so you get this piece. Okay, these other two pieces kind of go for a ride, they don't do anything. And the third piece that you have is I epsilon ijk sigma k, that is multiplied by pi I times pi j. Okay, so therefore you get epsilon ijk pi I pi j sigma k. Okay, now remember, in vector algebra, if you see a quantity like this, that epsilon ijk ai bj ck, then you will say that this quantity is a dot b cross c, right? That is the kind of expression you would get. Okay, so that is what is the second piece. That second piece is I times sigma upon 2m times cross product of pi I with pi j. Okay, or pi with pi. Okay, now naively you would have expected this pi cross pi to be 0, but that's not true here, because there's a gauge field sitting around here, there's a vector field sitting around here, and when you open this up, there are various terms, and many of them vanish, but not all. Okay, is this clear? Is this manipulation clear?
Yeah, I guess.
Okay. Yeah, here's a property of Pauli matrices that I used. Okay, fine. So let's look at this cross product and try to simplify that. So this cross product, you can open it up. You get one term which is P cross P, that is kind of trivially zero. You get another term which is A cross A, which is also zero. Okay, so only thing that survives is P cross A and A cross P. Okay, remember that these are operator statements. So therefore, when you write down P cross A, it means that P would act on A as well as P would not act on A and go across and act on phi. Okay, so therefore, when you write down terms, you find that out of the 4 terms that you would get, 2 terms just vanish trivially, P cross P and A cross A. And then there are 2 terms which survive, of which one term is P cross A and the other term is A cross P with the same sign. Okay. Now, when the P goes across, then it actually gives you A cross P with the opposite sign, and therefore the term which is A cross P actually cancels out. Okay, only term that survives is when P actually acts on A. That is the only term that survives, and that is written as I H bar times E by C nabla cross A. That is curl of A is the only term that survives here. Okay, is this manipulation clear? We can go over it once again if you want. So we can write down pieces step by step. P cross P is trivially zero because every vector is kind of parallel to itself, and therefore that would vanish. A cross A also has the same property. Okay, but now if you look at P cross A, that has 2 terms. P acts on A or P acts on phi. But when P acts on phi, it has to go through A, and because it's a cross product, it will flip sign. So that term is actually plus E by C A cross P acting on phi. Then there is a second term coming of this product, which is minus E by C A cross P, which will cancel with this piece that I just talked about. Okay, and the last piece is of course A cross A, which will cancel. So only piece that survives is when P actually acts on A and does not act on phi. Okay, and that is this piece. We know, of course, curl of A is magnetic field. So this is actually a term where this entire cross product written out here is just magnetic field. Okay, and thus we actually end up getting a Hamiltonian which looks like this. Okay, and you can see that there is a sigma dot B coupling sitting around uh, in 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 this Hamiltonian. Okay, now one important thing here is that that this is a coupling of spin to the magnetic field, and it comes with the factor EH bar upon 2 MC with sigma dot B. Okay, and this basically tells us that the spin gyromagnetic ratio is in fact 2. Okay, and the reason why the factor is 2 and not 1, if you look at this factor, then you would think that the answer should be actually 1. Okay, but the spin operator, if you remember, is written by as S vector is equal to sigma by 2. Okay, and since it is sigma by 2, the factor of 2 is actually soaked up in the definition of the S vector itself. So if you replace sigma by the spin operator, then it is E h bar upon mc times S dot b. Okay, so what you do is that you multiply and divide by 2, and then you write down E h bar upon 2 mc S dot b as a normal, as a usual coupling, but an additional factor of 2 multiplying it, which you interpret as the spin gyromagnetic ratio. Okay, so I suppose I should have just gone down. It's right here. Okay, that spin operator is defined this way. So you rewrite this entire expression in this particular form. Okay, so this is a usual factor. Okay, and this factor of 2 tells you that it is
Sir,
yes.
there is an extra H cross you have put because after it H cross is soaked up in sigma, right? To write S. So
Oh, okay, okay, fine. Yeah, yeah, that's right. Yeah, I'll remove that. Thank you. Okay, fine. So what we find is that I think I'll have the same error when I'll talk about angular orbital piece also. Probably I'll just continue uh, having H bar, additional H bars. I'll clear them up. Okay, so this is an interesting thing because you do experimentally see that the electron gyromagnetic ratio is actually 2. Okay, so hello.
Yeah, sir.
Sorry, the internet connection is again gone. So I'm back to my telephone Wi-Fi. So I think we were here when Aman told me that like there should be additional H bar that I'll remove. I said I think all of you were there at that time, no?
Yeah.
Okay. So only thing that I was saying was that we looked at the equation where we looked at the cross product piece, which is the last piece of the equation, and kind of manipulated and said that that is basically just coupling of the spin to the magnetic field. Okay. Now let's try to simplify the kinetic term piece and try to see how that expression looks like. Okay. So let's do that now. So this again expands. Now this is a dot product, not a cross product. So you get P dot P, A dot A, which are these two pieces. And then you get the cross dot product. I mean, well, weird way of saying it, but like P dot A term and A dot P term, which are written out here. Okay. Fine. So we had actually manipulated this. If you work in say del dot A equals 0 gauge, then you can kind of write down this expression as 2 times A dot P kind of piece, and can show that that is manipulation that you can do by assuming certain things like the external magnetic field in which this particle is moving is constant, and we will do that manipulation soon. But we will see that the gyromagnetic ratio, there is extra, and I'm not kind of rationing the gyromagnetic ratio, but like sorry for that. The gyromagnetic ratio of the orbital angular momentum is 1. In fact, we'll see in a moment. So what we have to do is to basically look at this expression, and in a convenient choice of gauge, you can write this as just 2 times A dot P. Okay. So in this case, we do exactly the opposite of what we did in the cross product, namely ignore the action of P on A and look at only the action of P on the spinor. Okay, that is why you get this term and not the divergence of the vector potential. Okay. Now suppose
Sir,
yes.
it is nothing but divergence A is 0.
Yes, that is the gauge that we are choosing. Yeah.
Yeah, thank you, sir.
Okay. So in the uniform magnetic field, if we consider that, then you can write down uniform magnetic field means B is just constant. Then you can write down the vector potential in this particular fashion. Okay, which is minus pi I hat plus x j hat, because the B is pointing in the z direction. Okay, so you can use that, and it is easy to check that if you substitute A in that fashion, then A dot P is basically B times LZ. Okay, this manipulation we had done it earlier, so that's why I'm not going through it. But if you really want to check, then you find that the dot product will tell you that x times py minus y times px is the expression that you will get. But x times py minus y times px is exactly the form of LZ. Okay, since B is in the z direction, BZ LZ is only the only single component that you get, simply because you are kind of choosing a specific direction for the magnetic field. If you choose the direction to be arbitrary, then of course you get the answer to be B dot L. Okay, so what we find is that we get an expression effectively, which is the total magnetic moment, which is written as E upon 2 mc times L plus 2s. Okay, so that's why the gyromagnetic ratio corresponding to the orbital piece is 1, and for the spin piece is 2. Okay, so so one important thing therefore is which is the outcome of the Dirac formulation is that you naturally get the spin gyromagnetic ratio to be 2. Okay, you don't kind of look at the experiment and put the number into the formulation. Okay, so this is was considered as one of the great triumphs of this formulation, because the theory gives you this answer and not the experimental data which asks you to put a factor of 2. Okay, good. So so like our earlier definition where we defined the slash operators, we define a slash operator in terms of this covariant derivative also. So covariant derivative is of course was the conversion of the minimal coupling piece, which was P minus E by C times A, to the operator form. Okay, so this del mu minus IE upon H bar C times A mu is just the operator form of the minimal coupling, and we write down d slash to be gamma mu d mu, exactly the way any other operator was written as the slash operator. Okay, and that is written in this form now. Okay, now you can check that the covariant derivative has the property that if you take the commutator of the covariant derivative, then of course if the index is same, it would just vanish, but if the index is different, okay, then you would get the field strength up to some normalization factor. Okay, so if you soak up, this normalization is basically coming from this covariant derivative piece. So if you write this factor out, then you actually produce electromagnetic field strength as a commutator of covariant derivative. Okay, and this is nothing special about, say, electromagnetism. Even if you study higher rank gauge theories, which is what you will do in, say, if you do a quantum field theory course, or if you do, say, particle physics course, then covariant commutator of covariant derivatives always give you the field strength of the corresponding gauge theory, corresponding vector theory. Okay, so this is of course only for the electromagnetism right now. Okay, fine. So what we'll do now is we'll go back to the Dirac equation written in a covariant form, which was I d slash minus mc upon h bar and times psi equals 0, and multiply this equation by I d slash plus mc by h bar from the left. Okay, so once you do that, of course, since the right part of it was itself 0, there is nothing special happening by this multiplication. But what we want to do is to actually open up this entire expression and write down the equation, whatever equation we get by opening this up. Okay, is that fine? Any questions?
So the F mu no that you have written, it is an operator.
It is an operator, yeah. Okay, because everything is an operator here, right? Del A, everything is an operator. So this also lands up as an operator, yeah. Okay. So in that sense, one is basically kind of forced to go to a field theory formulation of this entire setup. But yeah, we will kind of stop short of that. There's a separate course for it. Okay.
Yeah.
Okay. So now remember that when we are trying to manipulate P, maybe I should just step back a little. When we are trying to manipulate these quantities, sigma dot pi whole squared, at that time we have to use a sigma matrix identity, which is written out here. Okay, we'll have to kind of do something similar when we are going to do manipulation of product of two d slashes. Okay, so you have a d slash here and a d slash here, so you get basically gamma mu d mu, gamma nu d nu. Okay, so you get a gamma mu here and a gamma nu here, and you need to kind of write down simplified expressions for these quantities. Okay, so we'll use the following expression. There is a 1 missing here. I thought I looked at this stuff, but okay. Yeah, this is 1/2 actually. Okay. So gamma mu gamma nu is equal to half commutator plus half anti-commutator. Okay, it's kind of a trivial statement. If you really open this up, then you get half of gamma mu minus gamma mu plus half of gamma mu, which would add to the first term, plus half of gamma mu, which will cancel the second piece of this. Okay, so which is what the left hand side is. But we know that the anti-commutator of this, I'm sorry, it's written in wrong order, but anti-commutator gives you G mu nu, and the commutator would give you sigma mu nu. Okay, now notice I'm using the notation sigma mu nu and not gamma mu nu because I'm using the decomposition of this into half of this plus half of that, and not I by 2. Okay, now, since I don't have anything, you may think that I could choose whatever I want, but that's not what I'm doing. Okay, so because of that, this sigma mu nu has a little different hermeticity property, but it doesn't matter right now. Okay, we are not going to look at every component of it right now. Okay, but nevertheless, what we need to do is the following: that when you look at this gamma nu piece, then when you symmetrize gamma nu, then you are going to symmetrize the d mu d nu piece. Okay, are you with me? Let me do it, say it once again. So maybe I reduce the split. Okay, so now we see both the equations on the screen. Okay, I want to write d slash square piece as gamma mu times gamma nu times d mu times d nu. Okay, that is the way I want to write it. Okay, but when I write gamma nu as half the commutator plus half the anti-commutator piece, then the piece which goes with anti-commutator, okay, would have a d mu and d nu symmetrized because anti-commutator is symmetric in mu and nu. Okay, so you would have that piece symmetrized, and you can use that symmetrized piece and contract that with G mu nu because this anti-commutator gives you G mu nu. Okay, and therefore you get a piece which is d mu piece, basically with a factor of half. Okay, on the other hand, when it multiplies gamma nu commutator, then it is a commutator of d mu with d nu. Okay, but we know what the commutator of d mu with d nu is, that is f mu nu. Okay, we also know what is the commutator of gamma mu with gamma nu is, that is sigma mu nu. Okay, so therefore what we expect when you look at the antisymmetric piece of gamma mu nu, which is this commutator, it will give you sigma mu nu, and it will multiply the antisymmetrized part of d mu d nu, which is f mu nu, and that's why you get a term which is sigma mu nu f mu nu. This is the piece coming from this commutator. Whereas the piece coming from this anti-commutator is just square of the covariant derivative, and that is this piece. Okay. So are you with me on this?
There's a minus sign and del mu minus I in a mu by h plus c.
Oh boy. Okay. Yeah. Thanks. Thanks. I'll correct that. Yes, you're right. Okay. So by the time I came from here to here, I switched the sign. Yeah, I'll do that. That is just a typo. Okay. So what we find is that we get one piece which is the inner product piece, which exactly the way we got in the sigma matrix manipulation also. Instead of delta ij, now we have G mu nu, simply because we are doing covariant version. Okay, so that piece gives you the squared object, and epsilon ijk sigma k kind of piece, which is now written as sigma mu nu, gives you this piece. Okay, in the polymetrics version, you got only the magnetic field, but now you get two pieces. Okay, you get this magnetic field piece, which is the same as what Pauli had written down. Okay, and you get this additional piece, which is the electric field piece. The way to understand this electric field is to actually try to work in the rest frame of the electron. If you work in the rest frame of the electron, then what happens is that in the rest frame of electron, the nucleus is moving. Okay, or I mean, since we are doing hydrogen atom. But if you are doing any electromagnetic field, then the source of the electromagnetic field would be moving, because the electron is rest in its own frame. Okay, so but that original source was only producing electric field. Okay, but that this electron would look at find as a magnetic field, right? Because a moving source would produce a magnetic field for the in the electron's rest frame. Okay, but that magnetic field has to be proportional to the electric field produced in the rest frame of the original of the source itself. Okay, so this term is of that kind essentially. Okay, that it is just a term coming from working in a different reference frame. Okay, fine. So first term, of course, we know it's a spin dipole coupling. We had seen it a few slides ago. In non-relativistic quantum mechanics, we refer to that term as the Zeeman coupling. Okay, whenever we studied the Zeeman effect, this is the kind of coupling that we looked at. Okay, it was there in Pauli equation, and we had gone through this thing. Second term has relatively less interesting physical interpretation, although it does have some effect which is called S state correction when one studies hydrogen atom. Okay, but we will not discuss this here, because doing this manipulation would kind of fill up about 6-7 slides for me. It's kind of a longish manipulation, but when we will study atomic spectra, we will get this S state correction effect in a different guise. Okay, so when we will get that term, I will basically point it out to you that this is something which we did not really look at it at that time, but now we see it. But to kind of summarize it in one line, if you look at these spin coupled to electromagnetic field, excuse me. If you look at the spin coupled to electromagnetic field terms in the non-relativistic problem, just a sec. Then then typically what you find is that those couplings have give contribution to energy only if the angular momentum values are non-zero. Okay, and so when we study atomic spectra, you will see that kind of stuff. Okay, now this piece, this kind of term contributes only when the orbital angular momentum is zero, which is what is called the S wave orbital. Okay, S orbital. Okay, and only in those cases would a term of this kind would contribute, and therefore you will get a formula which was initially written for L equals 1, 2, 3, but because of the correction of this type, you actually get a formula, get the same formula, but now it allows you to write down L is equal to 0 value also. Okay, when we will come to that, we will see. Okay, but this term contributes only when L is equal to 0, and it vanishes whenever L is not equal to 0. Okay, fine. So, so let's come back to the Lorentz force and try to see how we can derive Lorentz force from the expressions that we have. Now remember that if the charged particle is in the external field, then you typically have a generalized momentum, and we know in this particular case our generalized momentum is P minus E by C times A, and we want to determine the force. That means the rate of change of this generalized momentum is what we are interested in. Okay, so we look at d by dt of this. Okay, but we know that if you are looking at d by dt of that, that is same as a commutator of the corresponding operator with the Hamiltonian. So here is a piece. Okay, fine. So besides that, yeah, sorry, this should have been a partial derivative actually. Okay, so okay, so that is the piece which is sitting around here. I did a typo here. So okay, but anyway, we can open this up, and when you open this up, then you can check that only piece relevant for the gauge field is the one which involves P in the Hamiltonian, because other pieces would just commute. Okay, and in the Hamiltonian also you have a gauge field, so that is that those pieces would only talk to the momentum operator here. Okay, this term also should continue here. I forgot again. Okay, but once you do that, then you can just manipulate these expressions, and you would find that you have a alpha dot p acting on A, and when alpha dot p goes across A, then that term in the commutator would just cancel out. Okay. Similarly, here you would get a alpha dot A piece with a del acting on it, but only when you look at the second term in the commutator. Okay, that means when the p is on the left and this operator is on the right. That's why you get a flipped signs here. Okay, this should have been E. There's too many errors actually. Okay, and this is the term that I should have written as a partial derivative, which continues out here. Okay, fine. So now you can check that this piece would give you the electric field. Okay, these two terms. Okay, that is the electric field, and this piece can be massaged to write down alpha cross B term. Okay, fine. So after you write that term, then you realize that you can write down, you can multiply and divide by C, and C times alpha is the velocity operator. Okay, and therefore you get a term which is E, which is the electric charge times the electric field, plus the velocity operator by C times B. Okay, now notice that in this expression everything is an operator, right? Because this was an operator whose time evolution is being looked at. Okay, and so therefore we have eventually found an operator expression for the Lorentz force. Okay, so remember we had some trouble kind of relating momenta to velocity operators and so on, but in this particular case, to get the Lorentz force, you get the entire system working out correctly. Okay, so that is the thing. So we have a operator form for the Lorentz force equation. Any questions here, barring the typos?
We can't particularly use this anywhere, right?
Use this means?
Like solve it for something, because like it's an instructive way of saying that the derivative of p minus e by ca comes out to be this, but
Yeah, no, but the thing is that, like, these are measurable quantities, no? Right? Everything is measurable here. So if you want to do an experiment, then you should be able to measure the rate of change of momentum of the particle and check each piece explicitly out here, no? Every term here is an observable, so it is experimentally possible to do the measurement. Is that okay?
yeah.
So in fact, like, just to give one example, like suppose you are using, say, cloud chamber, and if a particle enters a cloud chamber and undergoes a decay, and if you have applied magnetic field to the cloud chamber, it will produce a track, okay, which is proportional to the expectation value of this velocity operator, in fact. Okay, and that is a way, in fact, one has measured the charges of the decaying particle by actually looking at the appropriate tracks. Okay, so if you go back to like almost 100 years, when people studied decays of these particles using, say, cloud chamber or bubble chamber kind of experiments, it is this kind of equation which was used. The apply magnetic field measure the radius of the orbit due to magnetic field, okay, and determine the particle. Okay, so I have one small request. As you can see that, like, when I'm giving the lecture, I also notice, and I'm sure you also notice, innumerable typos. I try to correct them and put them back in the notes, but there is a chance that I would still miss out a few. Like, for example, today's lecture, I have minor typos, but several of them actually. So in case you people are looking at the notes again, and if you notice some of them, the typos are still there, please let me know. Okay. Is that okay?
Yeah.
Okay. Okay. Thanks. So let's look at the next thing, which is what is called the spin precision. And so we try to kind of start with our old equation that we had written down. The equation, of course, not written in this particular form, but what we had written down was that we introduced a spin operator in the system, and we wanted to write down a total angular momentum operator such that total angular momentum is conserved, but the spin angular momentum and orbital angular momentum is not conserved. Okay, and when we kind of introduced that operator, we said that d dt of that operator was minus c2c times alpha cross p, which exactly canceled the non-conservation piece which came from dl by dt expression. So that is the expression that I'm rewriting. Instead of writing s, I'm writing sigma now. Okay, but sigma is a spatial component of the sigma mu nu that we have been using. Okay, so there's a double jump in the notation, so I should kind of maybe go back and explain. Okay, so we have a sigma mu nu written as gamma nu commutator. Okay, I'll correct this, swap their positions just to be correctly stated. So sigma mu nu is a commutator of gamma nu, and if you look at the spatial component of the sigma mu nu, that will be sigma ij. Okay, that is a quantity which is gamma I gamma j commutator. But because it is a commutator, it is antisymmetric in I and j. Okay, and in 3 space-time dimensions, second rank antisymmetric quantity can be written as first rank antisymmetric quantity by multiplying epsilon. For example, Fij, which is the spatial component of the electromagnetic field strength, we write down Fij in terms of Bk by multiplying that by epsilon ijk. Okay, so epsilon ijk Fij is equal to Bk. So we will do the same thing with sigma. Sigma ij, we will write that as epsilon ijk sigma k, and now sigma k carries a single index, and that's why we would call it a vector. Okay, which is what we have done here also. Okay, so that is this sigma vector, which is epsilon ijk sigma jk. That is a kind of expression, but it is like a vector. Okay, so this is the non-conservation of the spin angular momentum. Okay, and we'll start with this and ask what happens if I study the anticommutator of this operator with Hamiltonian. So if you do that, then we will write, of course, if you are working in the presence of presence of electromagnetic field, excuse me. If you are working in the presence of electromagnetic field, you will replace this P by pi. So therefore, the anticommutator that we would look at is the anticommutator of this kind. In this, of course, you have alpha dot p piece, alpha dot pi piece with alpha cross pi piece, which is expression for d sigma by dt. Okay, of course, there's a beta mc squared piece also, but remember that sigma is written only in terms of alpha, and since we are doing anticommutator and beta and alpha anticommute, that piece does not contribute. Okay, so therefore, in spite of having another piece, that is not going to be relevant for us. Okay, fine. So yeah, that's what I wrote. Now, what happens is that alpha matrices also satisfy similar relation as the Pauli matrices. It's kind of obvious because alpha matrices are kind of off-diagonal Pauli matrices, so they will essentially follow a relation which is what the Pauli matrices also satisfy, but nevertheless it is here. Okay, so if you write it down in this particular form, then you can substitute that relation into this expression. Okay, so now we have to do two things. First thing is that we write down this cross product by using the epsilon tensor. Okay, so that is this expression, epsilon epsilon L M N alpha M P pi pi M alpha N. That is the kind of expression that we are writing down. Okay, then there exists another expression which is the dot product here, which is written in terms of alpha I pi, which is this term. Okay, then you get alpha I and alpha L, and then the alpha I alpha L product here involves an anti-commutator, and that requires you to write down this expression, which is epsilon I L j sigma j. Okay, so what we do is that you convert the anti-commutator pieces using this cross product into a commutator piece times the I epsilon I j k sigma k piece. Okay, so this part is coming from the product of alpha matrices, and this part is coming from the cross product of alpha with pi. Okay, so once you do that, then you get an expression which looks like this. This commutator needs to be computed now. Okay, but we know what this commutator would do, right? Because this is like a part of the covariant derivative, only the special part of the covariant derivative. Is that okay? Right, remember we had written down D, and we said that the commutator of D with itself gives you field strength, right? But now you restrict that to only the special component. You say Di, Dj, okay, that will give you Fij, right? That is what we are going to eventually get in this computation, right? So the piece that is important here is basically to realize that this cross product requires one epsilon, which is epsilon LMN. This dot product, of course, has only one index on alpha and the same index on pi. Okay, but then alpha product would involve another epsilon. Okay, and that is a piece that is being written down here. Okay, so now what we are going to do is to use the commutator of two covariant derivatives. Okay, so but any questions here? Yes, straightforward manipulations, you could do them, it will take probably 3 steps or 4 steps in between. Maybe not even that. Okay. So as I said, that commutator of two covariant derivatives would produce the electromagnetic field strength. So we'll just look at the special component of it. It will produce a magnetic field for us. Okay. So what we get is something like this. Okay. So now notice that we are actually going to get FIM by using the commutation relation that we have been using. Okay. Yeah. It's okay. We have seen it just a minute ago, but I just wanted to get it on the screen. It's here. Okay. So if you use I and M, then you get FIM, which is what we expect. But remember, just a few minutes ago, I was saying that FIM is an antisymmetric tensor in 3 spatial dimensions. And in 3 space dimensions, you can replace the second rank antisymmetric tensor by a vector. Exactly the way the magnetic field is a vector. In magnetic field should have been a second rank antisymmetric tensor, the way it is written in the relativistic form. But because of the spatial symmetry, we can convert that into a first rank quantity or a vector quantity, and that's what we'll do. So remember, now we already have two epsilon LMN, epsilon IL J, and then we get a FIM, and that we'll write in terms of B using another epsilon. Okay, so you get epsilon IMK times BK. Okay, so that is the total expression. We need to kind of just manipulate epsilon tensors. Okay, so there are various epsilon tensors. You can choose any two of them you want. So, and you will of course want to keep one of the epsilons free. Whether you, which one you want to keep is up to you. Okay, fine. So you look at the common, of course, when you manipulate epsilon, it has to have at least one common index. So you use that and manipulate this expression. We have used M to be a common index and written down this. Okay, so epsilon ijk, epsilon I lm is jlkm minus jmkl, and that is the kind of expression that we have used here. Okay, if you substitute that back into this expression, you'll find that this is just sigma cross B term. Okay, fine. So this sigma cross B term is basically the expression for the Larmor precision. Okay, so we find that Larmor precision term is basically related to the non-conservation of the spin and its anti-commutator with the Hamiltonian. Okay, so so we could after that I would like to start the hydrogen atom problem, but I think I'll kind of keep it for the next class, because I don't want to start it here and kind of leave it at halfway. But any questions here?
Sir, like when we write the angular momentum operator,